Hello everyone. In today's lecture, we are going to talk about serial port programming. Before I get into the details of this chapter, I just want to ask a couple of questions so that you can think about throughout the chapter, and then we can find the answers inside of this chapter. The first question is, how do we transfer data from one end to the other? The second question is, what type of communication channels we can use? The third question is, what kind of communication we can use? And the fourth question is, how do we transfer data, the hardware that we need to use, and what AVR is playing in this communication medium, or how can we use AVR in this communication. So let's get into the outline of this chapter, and then we'll try to find answer to these questions. So in this chapter, we are going to talk about serial versus parallel data transfer, simplex versus duplex versus full duplex, advantages of serial communication over parallel, and synchronous versus asynchronous communication, what is data framing, the data transfer rate and bits per second, how do we calculate, RS-232 standards that we are using, and AVR serial communication features, so special registers for these features. And let's get a start with the serial versus parallel data transfer. Now, in computers, there are two ways of transferring data. One of them is serial, and the other one is parallel. Now, when we think about serial transfer, we have got sender on one side, and we have got receiver on the other side. And there's one communication line that sends the data from one side to the other. So it actually transfers a bit after another. And when we talk about the parallel, we have got the sender, we have got the receiver, and we have got parallel lines 4, 5, 6, 7, 8. We have got these parallel lines that we can transfer the data 7 down to 0. So what is actually happening is it gets the data from the data bus and directly transferred to the receiver. Now, which one will be better? What we can say about these two is the parallel one, as you can see, we can transfer the data parallelly. So that means it's faster and it's easier. But when we talk about the serial one, we have to transfer one bit at a time, but it's cheaper as we are using less lines over there, and it's ideal for long distance. So what do we mean by long distances? When you consider parallel data transfer, we need a cable with either 8 or more lines. So generally the parallel data transfer happening with 8 or more lines, or conductors, wire conductors. And they have to be not long enough. So the cables shouldn't be long enough, because if they're long enough, it's actually causing a distortion or noise problems, which is affecting the signal transmission. And in the old days, one of the most used area of the parallel communication was printers and IDE hard disks. And each of these uses many wires inside of their cables. I don't know if you do remember parallel cables connecting to the printers and with the parallel ports and so on. Okay, it's actually transferring data in a short amount of time, but the distance over there is not great. So when we want to consider to transfer a device data from one device to another, which is a meters away or the kilometers away, we prefer to use serial communication. Okay, it's slow compared to the parallel one, but it's cheaper and it's only one line and it's not going to affect the communication or the bits that we are sending in there. So that's why the technology moved into the serial communication, and the parallel ports are not used anymore in most of the computer architecture or the system. So in serial communication, the data is sent one bit at a time, in contrast to the parallel communication, because in parallel the data is sent at a byte or more at a time. And it's actually what is happening. The information for the parallel devices is just grabbed from the 8-bit data bus or more and then presented to the 8-bit data bus of the device. And as we already said, this can only work if the cable is not too long, because long cables diminish and even distort the signals. And 8-bit data paths, if you want to use the cables, is quite expensive. So these are the reasons that we concentrate on the serial communication to transfer data between two systems located maybe in 1 meter to each other or maybe kilometers to each other. So let's see for the rest of these chapters how we are going to deal with this serial communication. So microprocessors or microcontrollers communicate with the outside world in one or many byte-sized data chunks. And as we already said, the printers are using 8-bit data parallelly, and if the cable is too long, it might be a problem, and so on. And the one thing that we need to consider, if we are going to use a serial communication, on one end, when we actually get the data from the data bus, 8 bits are coming in, but we need parallel to serial out shift register. Okay, and on the other side, we need to have serial in, parallel out shift register. Okay, so that's how we can actually use serial communication between the devices. This is really important. So that's actually going in there. Okay, so if we understand the difference between serial and parallel and know the advantage and disadvantage compared to each other, that's why the technology developed on the serial communication side, and this is what we are going to concentrate in this chapter. So I think we have answered one of our questions. What is the data transfer method that we generally use? And that is serial. Okay, now when we talk about these communication, let's say for long distances and so on, one of the most used important over there is a telephone line. So for telephone line, for a serial communication, it requires a device called modem. What is modem? Modem is actually, we can say that it's modulate. So modulates the signal, which means convert zeros and ones into audio tones, and demodulate, which converts from audio tones to zeros and ones between the two communication mediums. And doing that, we use two types of methods. One of them is asynchronous, and the other one is synchronous. So in serial communication, two methods are used, asynchronous and synchronous. What's the difference? The synchronous method transfers a block of data at a time, whereas the asynchronous method transfers a single byte at a time. And you can see from the literature there are different types of communication protocols or the softwares written for these purposes, and they're not really useful. So what they have come out is they built special ICs for serial data communication, and these type of ICs are normally called UART or USART. So two words which are important for us that we need to know and learn. UART is actually Universal Asynchronous Receiver Transmitter. Universal it's not gonna fit in there. Hang on. UART, Universal Asynchronous Receiver Transmitter. And USART is Universal Synchronous Receiver Transmitter. So we are going to talk about these in more details. But why I'm mentioning those now? AVR chips, the AVR microcontroller, has a built-in USART. So this is what we are going to talk about later in this chapter. Now, before we get into the AVR side, we need to understand one other thing: the communication channel types. Communication channel types, it's actually we can have a different types of communication between two devices. This is actually three types. So I'm just gonna show you what those are now. The first one is, we call it simplex. So what is simplex is doing? We have got the computer and we have got the peripheral on the other side. So with the simplex, we actually have one line going from one to the other, and we can say that data can move only in one direction. This is simplex. And what we are doing, we are actually sending a data block over there. So this is simplex. Then we have got another method which is known as half duplex. And engineers, please be careful. Please try to learn this because they normally ask this in interview questions. So with the half duplex, we have got again computer on one side, and we have got peripheral on the other. Now, as it says duplex, we have got actually maybe I need to get this bigger, hang on, because I want to show it in details. The computer itself has got I'm just extending that and extending this. So we have got transmit and receiver in it. Okay. And on the other side, we have got transmitter and receiver. So what is actually happening over there? We have got one line, but they're both either sending or receiving data from both of them. Okay, so it's not one-way communication. We have got data can move in both directions, but not at the same time. So if we are transmitting, other one has to wait for to receive it, and then it can transfer. So data can move in both directions, but not at the same time. Okay, so let's put the arrows over there that it can go both directions. Okay, so the last one, which is known as, I need to open a new page, full duplex. With the full duplex, again, we have got the computer, and we have got the peripherals, transmitter, receiver, and on the other side we have got the transmitter and receiver. And what is actually happening? Transmitter actually sends the data to the receiver online, and the transmitter on the other side sends a data to the other one. So it can actually transfer the data in both ways at the same time. So there are two lines over there. So data can be, data can move in both directions at the same time. So this is full duplex. And I'm just going to show you a couple of slides related to these in details. So this is what we already covered, the simplex, half duplex, and the full duplex. We have got the transmitters and receivers on both sides, but the half duplex uses one communication line, and we have to wait one to finish to start the another one. And with the simplex, it's just sending one side to the other. So the printer is a simplex, a communication channel that is used because we are just transferring something to printer. But nowadays it's more advanced version of it because the printer also sets some acknowledgement signals as well. So the half duplex is one line, and the full duplex we have got two lines so that we can transmit data in both directions at the same time. Okay, so please note these down and try to learn them because they are pretty important for rest of your life, and they normally ask this in an interviews. Now, the next thing that we are going to see is how these communication channels are using the medium. So with the simplex one is unidirectional. It's only the data block is sent from computer to the peripheral. With the half duplex one, as we are sending the data block with CRC codes, the peripheral is also sending the acknowledgement or not acknowledgement on the other side, but it has to be activated one at a time. And the full duplex one, it sends both the CRCs and the acknowledgement and the data blocks and so on, and it can also receives and transmits from the other side as well. So it can work in both directions. So I hope it's clear. If you have any questions related to this, note it down and ask me during the QA session. Now, the next thing that we are going to consider is when we talk about serial communications, we are actually talking two methods of serial communication. Either it can be asynchronous or the synchronous modes of operations in serial communications. Now, the difference between them, it's quite obvious as you know the difference if you know the difference between asynchronous and synchronous terms. The asynchronous, there's no clock pulse. With the synchronous, there is a clock and everything is synchronized with the clock. So with the asynchronous mode, clock pulse is not transmitted. The two sides should generate a clock pulse independently. The computer has one, the peripheral and has another one. But there should be a way that they are going to synchronize as we are not using the clock over there. And with the asynchronous mode, we can actually transfer a single byte at a time. And generally we call this universal asynchronous receiver transmitter, which we already said that. So with the asynchronous serial communication, we actually need some kind of protocol or set of rules to acknowledge each other that the received or transmitted data is actually what is received. Okay, so we have to be careful over there, and we have to understand how the data is packed in asynchronous communication. So how many bits is constituted a character, where the data begins and where the data ends. So we have to know this. So with the asynchronous mode, as we already got a clock on both sides and it's transmitted from one to the other, they are synchronized and one side generates the clock all the time. So we can send a block of data at a time. So as we already said, Atmega 128 or AVRs, they generally have universal synchronous asynchronous receiver transmitter ports. So we call that user port. and it actually supports both synchronous and asynchronous transfer. So we are going to see that in details later in this chapter. So when we talk about asynchronous, what we are actually saying is we are sending ones and zeros from one side to the other. So how are we going to synchronize the data between the transmitter and the receiver? As we already said, we need the protocols. So in these protocols, we have to say how the data is packed, how many bits we are sending in this package, and where are the beginning and the end bits, and where is the center of it. So we have to know each of these on both sides so that we can transfer data. And it's actually pretty simple. Why is it pretty simple? We just need to mention where the start bit begins and how fast the bits are coming. So we are going to see these two, how important they are and how we can transfer the data from one side to the other. Now, with the asynchronous serial data communication, which is one of the most widely used character-oriented transmissions, in asynchronous mode, each character is placed between start and stop bits. So I'll draw this. So what we are actually having is, let's say this is our this will be the best way of drawing this. So generally we have got one start bit and one stop bit. Let's say this is actually the start bit because we are transferring LSP to MSP, and stop bit. So what is happening over here? We place the character between these two bits. Okay? And this is actually called framing. So in data framing for asynchronous communication, the data, such as it can be ASCII characters, are packed between start bit and stop bit. Now, the start bit is always one bit, but the stop bit can be 1 or 2 bits. And the start bit is always 0. So it's always low. And the stop bits is always 1. So when we are sending, the receiver side looks out for the start bit, which is low, it's coming in, and then it waits for the data, and then looks for the stop bit. So how this is done in asynchronous USART? So the user uses 16 internal clock to sample the start bit. Okay, and the incoming data is continuously sampled until a falling edge is detected. So we're sampling, and then suddenly falling edge starts to come in. But Is this really the start bit, or it's something else that we are sending? So how does it going to understand? What is happening is, once the falling edge is detected, the receiver waits 6 clocks. So 1, 2, 3, 4, 5, 6. And then it begins sampling. So what is happening is, 1 clock before the expected center of the start bit, which is somewhere here, 3 samples are taken. So 8, 9, and 10 are taken as 3 samples. So if 2 or 3 are detected as high, so if one of these samples are detected as high, then it's looking for another falling edge. That means it's not a start bit, so we're still sampling and waiting for the start bit to come in. And if the result is low for that 3 samples that we have taken over there at the middle, that means we have got the valid start bit and we can start sampling the data. And data sampling starts from the center of the start bit and it takes 16 clocks. Okay, and we start to receive the first bit, as you can see over there. And once we got the characters, we check for the stop bit, and then we look for another start bit, and so on. So this is how asynchronous USART is working. Now, as we already said, on the right hand side, we need a start bit and stop bit, and we have got a character in between there. Now you can see that this is in detail with the timing waveform. So we start, this is our framing, which is called framing. We have got the start and stop bits. Start, it's always start with the space, which is 0. Then we have got the characters. This is actually representing ASCII A for 1 hex. So we have got 1, 0, 0, 0, 0, 0, 1, 0. This is least significant bits. That's the most significant bit. That is how we are actually transferring data from one end to the other. Okay? And in addition to these start and stop bits, we can also add a parity bit. If you do remember from the logic design, we can use parity bit to make sure that the received data is the correct data. So we can use either odd or even parities over there. And then each frame is ended by a 1 or 2 mark, which is called stop bits. And they are always high. So this is how we can use asynchronous communication using a framing, and we can transfer data from one side to the other. Now, so we understand the difference between synchronous and asynchronous. Now we understand how asynchronous is working and transferring data with using some kind of protocol with the start and the stop bits and so on. Now, the next thing that we need to ask is how fast or how are we transferring these data from one end to the other. So in communication of these type of devices, it requires extra signal bits that are not data. So this causes the data transfer speed and the baud rate to be different. Now, data transfer speeds or the baud rate that we are going to talk about. The rate of data transfer in serial data communication is stated in BPS, bits per second. And another widely used terminology for BPS is the baud rate. However, the baud and the bit per second are not necessarily equal. This is because the baud rate is the modem terminology and is defined as the number of signal changes per second. And in the modems, sometimes a single change of signal transfers several bits of data. And as far as the conductor wire is concerned, the baud rate and the BPS are the same. And in this chapter, we are going to use BPS and the baud rate interchangeably. Now, the baud rate is a measure of symbols per second or signal change per second. And we need to know and understand the formula because we are going to use a lot. So the actual data transfer bits, BPS, is given by number of data bits divided by the number of frame bits multiplied by the baud rate. Now, consider an asynchronous serial I/O system with no parity, 1 start bit, 8 data bits per frame, 1 stop bit with 9600 baud. So what is the data rate and the character rate? Now, the data bit rate we just need to use the formula given to us. So what is the number of data bits? The number of data bits, we have got 8 bits of data as it says. So what is the number of frame bits? The frame, it's actually containing start and stop. We don't have any parity, so we don't need to add anything over there. So 8 plus 1 start plus 1 stop is actually 10 bits. So that means data bit rate is going to be 8 over 10. Okay. So BPS is equals 8 over 10 multiplied by the baud rate, which is 9600. So this is actually going to give us 7680 bits per second. Okay, this is the data bit rate. To find the character rate, so we just need to use the baud rate, which is 9600, and how many bits per character? In total, we have got 10 bits per character. That means that is going to be 960 character per second. And this is how we can calculate the character rate. And you can find the same examples over there. Now, the one thing that we need to concentrate now, so we know the data rate, we know the asynchronous mode, we know the synchronous mode, and so on. There should be a way of or a standard to use in these communications. And why do we need that? We need to allow a compatibility between the devices. So various manufacturers can build up these devices with the serial communication, but they need to have some standard communication protocol. They need to have some kind of same type of transmitter and receiver sites, and they have to have some kind of protocol. So in 1960, Electronic Industries Association set some standards, which is called RS-232. Now, in 1963, they have modified and they call it RS-232A, then RS-223B and C in 65 and 69 respectively. But in this chapter, we will just use RS-232 to make our lives easier. And RS-232 you can find in the markets or you can check from the data sheets. That is one of the most widely used serial I/O interfacing standards. And this standard is used in PCs and numerous types of equipments. And the only drawback of this standard is, as it said around 1960s, before the TTL logic family, the input voltages and the output voltages are not compatible with TTL. So, for example, in RS-232, 1 is represented by -3 to 25 volts, while 0 bit is represented by +3 to 25 volts. And there's a making -3 to 3 undefined in this case. So for this reason, when we consider RS-232 and when we want to use RS-232, if you want to connect it to your microcontroller system, we must use some kind of voltage converters. And one of the most used voltage converter is MAX232. So it converts the TTL logic levels to RS-232 logic levels and vice versa. And MAX232 IC are commonly used as a line drivers, and you can find lots of variations on the market. Now, let's get into the RS-232 standard. So RS-232 defines signal levels, connectors, pin assignments, plus other things like protocols. And we have got these on every PC recently. So the serial port or serial interface connector, which is a 25-pin connector, then this is reduced into the 9 pins, which I'm going to show you in the next couple of slides. Actually, we are using a minimum of 3 pins, which is a transmit, receive, and the ground reference. And RS-232 categorizes the data communication in 2 types. The data terminal equipment. So data terminal equipment refers to the terminals and the computers that sends and receives the data. And data communication equipment is actually refers to the communication equipments like modems that are responsible for transferring the data. Okay, so these are the 2 things that we need to understand the communication equipment, and this is also a interview question. So please note it down. You might get a question if you are working in the embedded industry and you are having a RS-232. What's the difference between DTE and DCE? Okay, so DTE, TXT transmit and RXT receives, and DCE, TXT receives and RXT transmits. So +12 logic 0, -12 logic 1. So we need some kind of conversion before we need to use. So DB25 is the larger version of the older version of the connector for RS-232. Now this has reduced to DB9, and the most of the time these are the 3 pins that we are interested in to connect things together. So receive data, RXT, transmit data, TXT, and the signal ground GND. So the rest, it can be used, but most of the time we are using on this, and in this chapter we will concentrate on this. And nowadays USB is replacing the serial communication ports on PCs, and you can find these RS-232 pins with the old computers and with the microcontrollers and so on. So as we understood the communication protocol or the standard that we are using for serial communication, now we can move on how these connections are going to be done. So null modem connection, it's actually showing us how DTE, the data terminal equipment, and how they are connected together. So the TXT of one side is connected to the RxD of the other side, and TXT of the other side, it will be connected to the RxD of the other side. So this is a null modem connection. That's how it is known. Now, the next thing that we are going to proceed is the protocols and the flow control of these. The protocol is a set of rules making connections and the messaging proper, and the flow control is a method of stopping and restarting the data transfers. Now, there are some standard protocols in communication industry, and we'll go through those. So ACK and NAC is the flow control. So transmitter waits for acknowledgement from the receiver side before it's sending the next data, because you're transmitting and the receiver says, okay, I've got the right data, now I'm ready to receive the next block. That means this is acknowledgement, and it can be not acknowledged. So if the receiver is receiving errored data, or there is something that happened and it didn't receive the data, it sends a NAC. So the transmission is then repeated. And CRC, cyclic redundancy check, longer check field than one parity bit. So CRC, it can check and track the message history to find the errors in there. On-off flow control, receiver initiates or stops the transmitter by sending X on or X off messages. So maybe the receiver side is not ready, so it can control when it is going to receive the new data and so on. And the break signal, it used to break or abort the transfer in midstream, or it can wake up a sleeping receiver. So these are the protocols and the flow control. Okay, so the next thing that we need to consider is, now we know the serial communication, the types of the communication, and the devices and the standards that needed for this communication. How AVR is going to play a role in this communication protocols. Now, as we already said, with the RS-232 standard, as it has invented in 1960s as a standard, the TTL logic families were not available at that time. So it is the original RS-232 connector is not compatible with standard TTL logic. So if you want to implement, or if you want to use RS-232 standard connector, we need to use a converter or a line driver, which we already said we need to use MAX232. Now I'm just going to show you how we can make a connection, the null modem connection, between the DB9 pin with the MAX232 and the Atmega itself. So let's say we have got our Atmega microcontroller on one side. So Atmega 128, it actually got on port D and E 4 pins. So PE0 port E has got RX D0 and PD2 has got RX D1. And on the other side, PE1 is actually TX D0 and PD3 has got TXD1. So we have got 4 pins on Atmega 128 that we can use for receive and transmit using RS232 standard. Now, in the middle of these, we have got the line driver, which we call it. So this is our MAX232. And with the MAX232, which you are going to see in a minute, we have got transmit and receive pins on the both sides. So one of the pins, which is T1 in, is going to connect to, let me select one of these, the receiver side of the Atmega. And on the other side, we have got R1 out, and that is actually going in to the transmit side of the Atmega. So the null modem connection, the receiver is connected with the T1 in, the transmitter part of MAX232, and the transmitter of Atmega is connected to the receiver side of the MAX232. Now, this is actually pin 11 and this is actually pin 12 on MAX232. Now, on the other side, we have got DB9 connector. Okay, in this DB9 connector, which we already seen it, if I go back, so the pin 2 and 3 is for transmit and receive. 2 and 3 is there. Okay, these two are used for transmit and receive. So pin 2 and pin 3, and pin 5 is this ground. So pin 5 is going to the ground. Now, how it is going to be connected to MAX232? Again, it's similar to a null modem connection. So pin 2, which is the receive pin, let's say RX, and pin 3 is TX. Now, the MAX232s, the transmit out, so T1 out pin, and receive 1 in pins are going to be connected. So the receive part is going to be connected to the transmit, and transmit part is going to be connected to the receive. So we are actually having a null modem connection. You have to know this connection between Atmega and DB9 because this is really important and you have to understand how it works. Okay, so going back to our slides, so make sure that you always satisfy this null modem connection. And if you go back, this is the MAX232 inside, so T1 in, which is over there, and then pin 12, which is R1 out, is there, so that's connected to the transmitter side and that's connected to the receiver side. On the other side, pin 14 T1 out is connected to the receiver pin of TB9, and so this is, just label those as well. This is pin 14 and pin 12, which is R2 in, R1 in. So we need to know these connections and how to perform them. You don't need to know the inside of that, but you need to know how we need to connect between DB9 and Atmega 128. Now, as we understand the connection of AVR with RS232 connector, we are going into the details or inside of AVR and how AVR is going to deal with RS232. So if you look at the next slide, in AVR we have a couple of modes for synchronous operation, and these modes are normal asynchronous, double speed asynchronous, master clocked synchronous, and slave clocked synchronous modes. So we can configure with the AVR serial programming registers that we are going to see in a minute, and we can do any of these, we can use any of these modes to perform the operations. So with the full duplex operation, with the configurable high resolution baud rate, serial frame sizes, 1 or 2 step bits, or even parity generation and checking, frame error detection, and multiprocessor modes are going to be covered in this section. And we generally focus on the asynchronous mode to connect AVR to the PC. And with the USART or the serial programming, we can have, in AVR provides us 3 interrupts: transmit complete, transmit data register empty, and receive complete. So we can use these interrupts to wake up the processor of doing what it's doing and get the NIV data or transmit the NIV data and so on. And in AVR we have got 5 important registers that we need to configure to perform USART operations. So UBRR is actually known as the USART baud rate register. So we need to calculate the baud rate that we want to have, and we have to put that value into UBRR register. And the next one is user data register. Data register, so if you want to receive or transmit a data, this has to be written into the UDR, or it has to be read from UDR register. Then we have got 3 control registers: user control and status register A, B, and C. And we are going to see the configuration of these individually. Now, if you look at inside of the AVR, this is what we are going to see for the organization of the AVR. So we have got the control registers, and we have got the clock generator over there to generate the baud rates necessary for the transmission, the transmitter part, and the receiver part. Okay, and they have got their own TXT, RXT, and the clock bits coming in, the pin controls, the receive control, the shift register for the transmit and receive, UDR on both sides, and the baud rate generator has got their own UBRR register. So clock generator XCK active in synchronous mode only if you want to use a synchronized. Transmitter and receivers are over here, and we can use AVR in any modes. Now, if you want to generate a clock, this is what we are going to see inside of it. Now this part, which is showing XCK pin and so on, over here with the multiplexer and so on. Now, this one for the multiplexer in UM cell is actually selecting the operation. So if we are going to use this part with the clock input and so on, it's going to be a synchronous operation if it is 1. If it is 0, we are going to use asynchronous operation where we need to calculate the baud rate from the baud rate generator and fed in to the TX clock and RX clock. Okay, so the formation, I think, is pretty straightforward. The multiplexer is actually helping us to decide if we want to use the synchronous mode when it is 1 or asynchronous mode when it is 0. And how do we set that? We set that inside of that UMSEL bit, which is in the control register C. Then U2X in the control register A, it actually selects the double speed TX in asynchronous mode. So you can select the double speed or a normal speed operation. As you can see, the clock dividers over there. And DDR XCK, it actually chooses between the internal master mode and external slave mode clock in synchronous modes of operation. Now, UBRR, which is the first register that we need to consider for AVR to calculate the baud rates. Now, inside of the UBRR, we need to find out how the baud rate needs to be calculated. And both the receiver and the transmitter side has to agree with the baud rate. Now, the baud rate generator is actually using a down counter which runs at the system clock to count from UBRR value to 0. So we set the UBRR value, it goes down to 0, then it loads the UBRR again. So when each time it reaches to 0, baud rate clock is ticking. And the final transmitting clock, it can go from 2, 8 or 16 division depending on the modes. So those modes are all given on this table. And we need to know these formulas to calculate the baud and the UBRR. So for example, for asynchronous mode, normal mode, which is U2X is 0, we don't want ultra speed over there, the baud can be calculated based on the frequency of the clock divided by UBRR plus 1 multiplied by 16. So UBRR value is, if it is given or if you know it, we can easily calculate the baud. Otherwise, if you want to calculate the UBRR that we need to load for that register, we just need to divide the frequency of the oscillator by 16 baud. The baud rates are normally given for the hyper terminals that we are using, minus 1. If you want to use a double speed, which is U2X is 1, this is rather than 16, we are just using 8. And if you want to use synchronous master mode, this is 2. Okay, so the formulas are all similar to each other. The asynchronous normal mode is using 16. The double speed is using 8, and normal synchronous master mode is using 2. So what we need to do, we first calculate the UBRR value, and then based on that we can load the UBRR register NH and LL based on the values that we have got. So for example, with the PC baud rates of 1200, as we have, let's say we have got, so the oscillating clock is 10 megahertz, and we have got the baud as 1200, and let's say we want to use in normal mode. So in normal mode, all we need to do for UBRR is equals 10 times 10 to the power 6 divided by 16 times 1200 minus 1. And this is actually going to give us 519.83. And what we generally do is, based on the calculation, as we are not going to include a fractional numbers into the register, we just get the integer part. So 519, it's 83. I can round that to 524 UBRR, and I can use that value in UBRR register. Okay, so this is one of the registers that we need to set it up. Now, as I already said before, and I'm gonna set it again, the most important thing in embedded systems is actually to understand how are we going to set these registers up. And if you understand how to set them up, it's pretty straightforward to write a code for it. So now we understood how UBRR is going to be set. Now with the baud rates, there's a baud rate error calculation. So as you can see, the actual baud setting is often an approximation of the real target. So when we calculate the UBRR, the result may not be integer, as you can see from the example over here. But we can only load the integer values into UBRR, so there will be an error rate over there. So the error is actually can be calculated as the calculated value, which is in this case is 519.83 minus the integer part, which is 519 divided by 519, and this will actually give us how much is our error rate is. Or you can just use the calculated baud rate minus the desired baud rate divided by the desired baud rate will give us also the error rate. So what we can generally do to omit these baud rate error, we can use specific crystals like 11.0.592 megahertz or 7.3728 megahertz and so on. That's also possible. So before we move forward, I just want to do a couple of examples so that we can understand how are we doing these calculations. Now, so with the frequency of the clock, which is 8 megahertz. Find the UBRR value needed to have the following baud rates. So first of all, let's start with 9600. To calculate the UBRR, we need to have the equation of FOC divided by, so I'm assuming these are in normal modes, and let's say the baud rate. Minus 1. So we can actually say for the first one we have got 8 times 10 to the power 6 divided by 16, and the baud rate is 9600 minus 1. Okay, and this will give us, if you want you can calculate that as 52.08 minus 1, 51.08. So as we can just get the integer part, that is going to be 51, which is equals to 33 in hex. So we can load that into UBRR. And you can repeat the same thing for 4800 or maybe 2400 and so on. You just need to change the baud rate and you can find the UBRR values necessary for that operation. So I hope this is clear. And now we are going to carry on with the frame format. Now the frame format, as you can see, we have got the start bit, which is always 0 or low. Then we have got data bits 0 to 8. And we have got the parity bit, even or odd parity. And then we have got stop bit, which is always high. It can be 1 or 2 stop bits. And for the idle, that means there's no transfer on the communication line for RXT or TXT, and idle must be high. So if the parity is enabled, even an odd parity can be calculated using XOR equations, which we have seen in logic design last year. Now, to detect an error, so by checking the errors in there, we can actually set the acknowledgement and not acknowledgement protocol for physical layers. So two types of errors, the frame error and the data run errors can be considered here. So the frame error occurs when the receiver is expecting the stop bit and does not find it, also known as synchronization failure. So if you don't find those, that means there's something wrong in the data that is transferred. and that gives an error. And data overrun error, data was not removed in the receive buffer before another byte came and overwrote it. So when you receive that data, that has to be directly transferred and cleared before the next one comes in. Otherwise, it will overwrite it and you will lose the first data that you have received. Now, the next register that we need to consider after UBRR is UDR, which is the USART data register. So in AVR, to provide a full duplex serial communication, there are two shift registers referred to as transmit shift register and receive shift register. And each of these shift registers has a buffer that is connected to it directly. Now, these buffers are called transmit data buffer registers and the receive data buffer registers that we consider. And they share the same I/O address. So we have to be careful over there, as they are sharing the same I/O address, which is UDR. We cannot receive and transmit data using UDR at the same time. So what we do, if you want to receive, you set the RxD pin, or if you want to transmit, you set the TXD pin, and we actually read UDR register into receive shift register, or if you want to transmit, we write into UDR register and that will be transmit into the data buffer and then transmit shift register. Okay, so this is how we can use UDR as a part of AVR registers. Now, so UDRN and UDRN, RxPN or TXPN, they have the 8 bits values over there, and that's how we can read these. Now, the control register, we have, as we have already said, we have got 3 control registers over here. So UCRNA is the first one, and it's actually have different functionalities in USART. So for example, RxCN, user receive complete. So if there's an unread data in the receive buffer, enabled with receive mode and can generate a receive interrupt. Or TXCN, bit 6, transmit complete, entire data has been shifted out, automatically cleared with the transmit interrupt generation. UDR-EN, USART data register empty. That means the UDRN is ready to receive the naive data. And error bits are valid until UDRN is read, so, and it should be set to 0 when writing UCRN. So FEN, DRN, and UPN, frame error, data overrun, or parity errors, they are all in control register A. If you are writing, they have to be 0. And U2XN, if you want to have a double speed of the USART in asynchronous mode, you have to set that. And MPCM is the multiprocessor communication mode, means some frames will be ignored if they do not have the correct address information. So this is register A. Register B, we have got some interrupt enable flags over here. So complete interrupt enable, TX complete interrupt enable, UDR interrupt enable, so data register MT interrupt enable is there. Receiver enable, so it's overrides normal port function of RxD pin. Disabling flushes receiver buffer and invalidates the error bits. And TXEN transmitter enable overrides the normal port function of TXD pin. If disabled, the ongoing transmission is finished first. And UCSZN2, That's the character side. This bit is combined with the UCZ1 down to 0 and sets the number of bits used by the transmitter and receiver. And the received data bit 8 and 9 bit of the received data read before UDRN, and transmit data bit 8 and 9th bit of the transmit data written before UDRN. So if you want to have a bigger data than 8 bits, you can use these bits RxB8N and TXB8N, and we can write an extra bit in there before UDRN. So the last register that we are going to consider is the UCRNC, and over here we can select the user mode, so asynchronous or synchronous. The parity mode, even parity, odd parity, can be set in UPMNs. And UBSN, stop bit select, so the number of bits to be inserted for stop bit. These are all can be configured in the control register. And of course the character size, as we already said. And so the 5 bits, 6 bits, 7 bits, 8 bits, they can all be set with UCZN. If you want to use a 9-bit, you can just set it to 111, and over here you have to put that 9th bit over here. And UC polan, clock polarity, data and clock edge relationship in the synchronous mode. So if you're using, you can say the positive edge or the rising edge or the falling edge of the clock is going to be considered. Now, so we have seen these registers. You can go them in details in the datasheet as well. But the best thing to understand how to use this register is to have an example related to it. But before we get into the examples, I just want to mention a couple of points which is important for AVR transferring and receiving. The first one is AVR serial port programming for receiving. So over here, the registers that we need to set and so on has to be configured accordingly. So the first point, USCRB, which is the control register B, has to be loaded with the value 10 to enable user receiver. So 10 UCSRB 0 hex 10 means 0001 0000. So if I go back, if we look at over here, that means receiver has to be enabled and the rest is 0. If you want to receive something, we have to enable the bit for, and we can enable the user receiver. Then second point, USRC register is loaded with the value UCSRC loaded with the value 0 hex 06. So 0000 0110. So this is for user receive. Now with the UCSRCC, that means UMCell is in asynchronous mode, which is selected 0. These are all zeros. Then we have got 0, and this is going to be 110. So 11 UCS ZN1 and 1 is actually going to give us 8-bit transfer. Okay, so async 8-bit and no parity and 1 stop bit. Okay, so if you look at here, USBSN is 0, UPMN is 00, so no parity bit, nothing else. no parity, and one stop bit. So that has set in UCSRC. Then we have to load the UBRR. So UBRR is actually the baud rate that we need to set. So we have to calculate that. Then we have to monitor RxCN flag. So if we receive any data, this can be done with the polling or using an interrupt. We have to check that if it's received or not. So to do that, we actually need to enable the interrupts to receive an interrupt from it. And then UDR register has the byte when RxC is raised. So whenever this is 1, that means UDR will read the value. And so we have to move the contents to somewhere, so because it can be overwritten as quickly as possible. And then we go back and start again. So we have to configure these three and then start again and so on. And for transmitting, so for transmission, UCSRB register is loaded with the 08 to enable user transmitter. So UCSRB is loaded with 08. So the transmit enable is just enabled over there. Then what we do, UCSRC register is loaded with 06 again, so asynchronous mode, 8-bit data frame, no parity, one stop bit like before. And UBRR is loaded with the baud rate for serial data transfer. So the character byte to be transmitted serially has to be written into UDR. So we have to load the UDR and then monitor UDRE bit of the USRC A to make sure that UDR is ready for the next byte. This can also be done with the polling or interrupts. And if it's a half duplex connection, may need to monitor TXCN as well. So transmit flag if we have got half duplex connection. Now we know the registers and how do we need to set them up. The next thing to do is to write a program for specific purposes and find out how this is going to be done. Right, let's open a new page. And let's start with the first program that we need to write. Now, it's asking for the crystal frequency of 8 megahertz. Write a program to transfer the letter G serially at 9600 baud continuously. So let's start with the baud. UBRR. So we have got 8 megahertz clock, and we have to divide by 16, which is going to give us 500 kilohertz, and that has to be divided with 9600 baud rate minus 1, and this is going to give us 52.08 minus 1, which is going to be 51.08, which is equals to 51. and 51 in hex is equals 0 hex 33. So this is what is going to be loaded into UBRR. That's done. Now, next thing that we need to consider, what are we going to set for UCSRA and UCSRB and UCSRC registers. Now, for UBRR, as we have got 0 hex 33, that has to be loaded in. And as we are going to transfer the letter G serially with 9600 continuously, so if we open up the registers over here, so based on that we can set them up actually. So what do we need to do? We need to set UCSRBN so UCSRB register, we need to set the transmit enable. So that's going to be 0 hex 08. So only that bit is going to be set. So 0000 1000 has to be set. Then for UCSRC, we want in asynchronous mode, 8-bit data frame, no parity and one stop bit. So we can just use hex 06 over there because that's the default. So we can say hex 06 on there. If you want, you can set them individually, it's up to you. And next thing to do for UCSRA, do we need to set anything up for that? We can actually check the TXCN, but it's not that important at the moment. So UCSRA, it's going to be all zeros. You don't need to set this up, it can be in default, so you don't need to worry about that. Now, so we have got all the register values that we need, and we know that if we want to transfer the data, we have to load into UDR register. Okay, so let's give a start and let's write down how this is going to be set it and used. Okay, I'll start with we need some kind of let's say let's start with LDI R16. So we want to set UCSRB register, so that's going to be only the TX enable pin. Okay, so I can say that enable transmitter, and then what we can do, we can out this on UCSRB R16. Then I'll do another LDI, again R16, and I can set UCSRC. So that is going to be 1 on UCSZ01, and also one on UCSZ00. So what we are actually setting over here, 8-bit data and no parity and one stop bit. Then what we do, we send this out to UCSRC, and that has to be R16, and that's done. And next thing to do is to set the baud rate. So R16 0 hex 33 is the value that we need to load. $9,600 baud. With 8 MHz clock. Out is UBRR0L. Actually, we forgot to say that this is 0 because we have to mention which one we are using. So this is 0L, and that's going to be R16. So we are loading into the low byte, as we don't have anything in the high byte. We don't need to load anything over there. And this is for 8 MHz. So we now set it for transmission, our registers. Then what we need to do, we can use polling over here to check if UDR is empty or not. So let's say again SPI S skip bit. So UCSR0A UDRE0. So we have to check this bit. Okay, make sure that it's empty so that we can transmit the next byte to it. And it can say is UDR empty. Okay, then our jump again. If it's not empty, we have to go and check again. Otherwise, if it's empty, LDI R16, we have to load the character G over there, and then out on UDR0 R16. So let's write a couple of comments. Wait more, and we can say send character G to UDR, and then R jump again. So if that is done, we can send the next character, or we can keep sending the same character as it says in the question. So This is a simple program, and we can set the UCSR 0B, UCSR 0C, and UBRR 0, and we can monitor UDR and send the character G from the AVR pin. We can also do this using a C programs. Okay, so this is assembly 1. With the C program, it's actually the same thing: 8-bit data bit, 1 stop bit, 8 megahertz, 9600. So we have got the same values over there for the registers. So only thing that we need to do, we can use a USART init as in a separate subroutine, and use USSR 0B can be set using TXN 0. Yep, and UCSR0C can be set, so we are setting that to be an 8-bit, and UBRR0L for baud rate as hex 33. And then we can use this and send this we can use to send the letter again if you want, and this is done in the example 3. So all we need to use, same the subroutine, we can just use over there, we can initialize it, and then we can monitor the UDR 0 and send the value. So USART init, which we already done it over here, can be just copied and pasted over there. Then monitor or poll for UDR, wait until it's empty. So if UDR is empty, then transmit the character. And in main, you can just initialize the USART, then you can just use the subroutine USART send character G, and that's it. We can just call these two subroutines and we can perform the function over there. And one other example, assuming that the frequency is 8 megahertz, write an assembly program to receive the bytes of data serially and put them on port B. Set the baud rate at 9600, 8-bit data, and 1 stop bit. Use receive complete interrupt instead of polling method. Okay, so the only difference is of what we have done. We want to receive something compared to transmit, so we have to change UCSR 0B to receive, and then the baud rate is still the same, and the port C has to be still the same because we are using 8-bit data and 1 stop bit over there. And the only difference is we have to use receive complete interrupt instead of the polling. So for interrupts to be receiving, which vector do we need to use? It says USART receive complete, it's over here, which is 0024. So I'm opening a new page over here. So interrupt vector is USART RX is address 0024. This is important because we are going to use that. Then UBRR, it's still 0 hex 33, and we want to enable the receive, so that's going to be 1 over there, and also we want to enable the interrupt as well. Okay, so we have to set this one to be 1 as well. So UCSR0B is going to be 1 0 0, then 1 again, then 0 0 0. Okay, so that is 0 hex 9 I think I missed one of the bits. So 1 0 0 1, then 0 0 0 0. So we need 4 zeros over there. So 0 hex 9 0 is the value. And UCSR C is going to be, again, we are just setting these to be 1 and 1, which is 8-bit data and no parity and one stop bit. So that's going to be 0 0 0 0, 4 zeros, the fifth 0, and then 1 1 0. So we have got 0 hex 0 6, and I think that's all we need to set for USART. But the only thing that we need to have over here, we need to receive the bytes serially and put them on port B. So we have to set the port B to be an output port. So we need to have DDRB to be 0 hex FF. Okay, so let's do that now, and let's write down the code for it with this configuration. So again, the important thing over here, as we are going to use the vectors, so at the beginning we can say dot czeg r jump main, or you can just use .org hex .org 00 for address 0, because we need to jump. And then we have got .org, the interrupt vector was in hex 24, so hex 24 will be our interrupt vector place. So we are going to serve the interrupt from there, and we can just say rjump when it reaches there, USART receive interrupt handler. I just call the function like that because this is what I'm going to call or use as a subroutine. Then somewhere else at the bottom, let's say .org start at 100. We want to write our main program. Again, we have to use stack as we are using an interrupt. So stack init, high RAM, low RAM can be initialized in there. Then LDI start R16. It's going to be 1 for RX enable and 1 RX enable, that has to be 0, and that has to be RX receive interrupt enable 0. So enable receiver out UCSR0B R16 and enable receiver and RxC0 interrupt. That's right, interrupt. Okay, then what we need to do, we have to do another LBI for setting up UCSR C. and that's going to be 1 UCSZ01 and 1 for UCSZ00, and that is for 8-bit data, no parity. Then out again, UCSR0C R16, no parity, 1 stop bit, just the rest of the sentence. And then UBRR value, again it's 9600 baud, so LDI R16 0 hex 33 9600 baud. Then that has to be in UBRR0L, and that's going to be R16. So crystal frequency is 8 megahertz. Then we have to set port B. Let's give some space. LDI R16 0 hex FF to be an output port, and out DDRB R16. So once we have done that, of course we have to enable the global interrupts. So SEI enables interrupts globally. Enable interrupts globally. Then we can use a wait over here, rjump wait, because we just keep waiting over there until we receive an interrupt. So we can say stay or wait here until a byte arrives. Then we need to write the interrupt handler service routine. So URX C interrupt handler. We'll start with. So what we need to have, we have to get the value from UDR into one of our GPRs in R17 UDR0. We'll actually transfer the value in UDR into one of the GPRs. So copy UDR to R17. Then what we can do, we can out this on port B on so on. So send R17 to port B and then return from interrupt. So I think that's basically what it is. We set it up, the interrupt for receiving, and we enabled the global interrupts. That was the only difference over here. And in the interrupt service routine, we just need to send the byte that we have received to port B. And of course, we have to specify the interrupt service routine vector from the vector table, which is given to us. So I think that's pretty straightforward for a what do you call for UART and the serial port programming. If you have any question on how to configure these registers and so on, but please make sure that you understand how are we configuring that. You can ask me during the question and answer session. You can send me an email and so on. I think next lab is all about these serial port programming and interrupts, and we can see that how interrupts can be used together with serial port programming. Thank you.